Welcome to the video on normal curves and z-scores. And we're going to talk today about what a normal curve is, or what it means to have a curve. And a lot of students think they know what that means. They think it means you just slide grades up because nobody did their best or did the best score, and you need to make sure that somebody got 100. And that thinking is actually not what grading on a curve really means. So we're about to see what that is. But let's talk about how we get curves that represent data. Okay, so we start with histograms. And a histogram has numbers on the x-axis, numbers on the y-axis. And if you want to understand what a histogram is about, it has to have labels. All right, so look at this one over here on the right. No words, no labels, no description. We have no idea what this data means. But over here, this says final scores. So maybe we're talking test scores, and it would go from 0 to 100, so that validates that idea. And then over here, numbers of students. So this is showing us the grade breakdown of some final exam. So, and I didn't make this chart, I just copied it off the web, so it's not my final scores. So here's what we got. Here's how you read something like this. So look at this little bar that's red. This says 20 on one end and 30 on the other. That means the scores in this column are somewhere between 20 and 30, although we don't know where. And then we look over and see how tall it is, and it corresponds to a height of 1. So this means one student scored somewhere between 20 and 30 on this test. Okay, if we jump over here between 60 and 70, we look up and we see that's at a height of 6. So 6 students scored between a 60 and a 70. In this really tall column, scores between 80 and 90. We've got, let's see, so each half box is about 1, so 12 and 1 makes 13 here. So about 13 students scored between an 80 and a 90. And we don't know how it's split up in there. We don't know if they're mostly close to 80, mostly close to 90, mostly in the middle. We have no idea. But this does give us a picture of the data that is easier to process than just a list of numbers, a list of scores. So here's a trick. Statisticians learn that if they connected, I'm going to connect dots to the left corner of each of these columns. We can connect these dots and come up with a curve that generally shows you the shape of this data. And here's what it looks like. Let me connect them. So I'm not going to be perfect, but it should be smooth. You know, if we had a computer or a calculator here, we could punch some numbers in and have it come up with the equation of this curve. And this curve is lumpy, and it's got a lot of data on the right side and very little data on the left, so it's not symmetrical. In fact, this over here is called a tail, and since the tail extends left, we would say this data is skewed to the left. Grades are often skewed to the left because 100 is a max and 70 is passing, and most students pass, and a handful of students don't pass sometimes, and so the scores on the left side below 70 are usually pretty small numbers. So grades are often skewed to the left. Other data sets are often symmetrical, and in real life it's not perfectly symmetrical, but even though we don't know labels on this graph, we can look at the shape. So notice how this has a tall peak in the middle. Not all the bars are equally tall, but a tall peak in the middle, and it gets shorter as you go away from the middle and ends up with a little tail on both sides. So this, I'm not going to draw dots on every bar, but this generally would look more like a bell curve, which is a symmetrical curve. It has a, oh, that was terrible. Well, that tail really should be way down here because the data goes all the way down. But it's somewhat symmetrical, and this is what we would call a bell curve. And named after a person named Bell, I suppose. Used to know the history behind that. But anyway, so we're going to call it a normal curve instead of a bell curve. And here's what we know. Statisticians have figured out that if you get a large enough data set, many of them are shaped like this. Many are symmetrical with a big peak in the middle and tails on the ends. And so when we take histograms and connect the dots and come up with curves that show the shape of data, we can begin to understand some things about that data. And so a distribution is a description of a set of data points. And if it falls in this generally symmetrical shape, if the histogram looks symmetrical like this, we can use that shape to help predict what percentage of the data falls in different number ranges. So we could predict future happenings, perhaps based on past numbers, which I think everybody is familiar with that idea behind statistics. So a normal distribution, and an official definition here, is, and that's be off the line. Okay, so a bell, and I'm going to put that in quotes, bell-shaped curve that shows how data is distributed from the mean or around the mean. Okay, So let me show you what some of these symbols mean, because not all of this has been defined, and you'll understand this picture a little bit better. So here we've got this weird looking symbol here. This is the Greek letter mu. It is their M sound in their language, and it even looks a little bit upside down like a cursive M, and it stands for mean. The mean of a set of data is the average, okay, in the traditional arithmetic sense. This other symbol, this is a lowercase s called a sigma in Greek, and it's their S sound, and it stands for standard deviation. All right, so you've learned a little bit about standard deviation. It helps you describe how spread out a set of data is. Are all the values clustered closely in the middle, or are they spread out really far from the mean? In a standard normal curve, the mean is right up and down the middle, the tallest part of the curve. And we usually put the mean here, the actual number that represents the mean, right under that tallest portion of the curve. Now, you can calculate the standard deviation of a set of data and come out here and mark so many points above the mean. So whatever one standard deviation is, we count up and down from the mean and label that one standard deviation, and you can put a plus if it helps, the positive end, and then minus one standard deviation puts you here, and then add another standard deviation to the right. That would be data points between here and here would be between 1 and 2 standard deviations above the mean, and then 3 standard deviations above the mean, and then this little bitty tail up here. Same thing on the negative side, keep subtracting the standard deviation from the mean to get this number, subtract it again to get this number, subtract it again to get this number. Now, this is called the empirical rule. These percentages that are in this diagram, empirical, there we go. And in normally shaped data, about 34% of the data lies within one standard deviation above the mean, and about 34% lies within one standard deviation below the mean. So that's what the 34s are about. So how much of the data is within one standard deviation of the mean? Well, that includes both directions, so we're going to add 34 to 34 and get 68%. About 68% of the data is within one standard deviation of the mean. So for instance, if we have a set of data, maybe they're test scores, you can relate to that, and let's say the average test score is an 85 and the standard deviation is 5 points. So this would be a grade of 90, this would be a grade of 95, this would be a grade of 100. All right, and maybe there's some bonus points you could score higher. Well, one standard deviation below the mean would be 80. 2 standard deviations below the mean would be 75, and, or excuse me, yeah, 3 standard deviations below the mean would be a 70, and then maybe a few people scored less than 70 and would be in the tail down here. Can you see now 68% of the data means that 68% of people scored between 80 and 90. That's 5 points above or below the mean. Okay, so if I said that the standard deviation was 5 and the mean was 85, that's how you can relate to this in a set of numbers. Okay, so what percent of the data falls within 2 standard deviations? Well, that would be in this section and this section on either side, right? So here and here, and we would add all 4 of these together. 13.5% lies between 75 and 80, and 13.5% lies between 90 and 95, and then the original 68% is here. So when we add those together, we get 95% of the data. All right. And then what percent of the data falls within 3 standard deviations of the mean? Well, that's everything but these 2 little yellow tails. Okay, so we could take our 95 and add the 2 greens to it. So 95 plus 2 is 97, and 2 more is 99%. All right. In reality, this is actually 0.15 and 0.15 on each end, so this is 99.7, but we're just kind of rounding here and taking it easy. So 99% of your test scores are going to fall between 70 and 100 for this set of tests. This is not every test out there. This is the results after a test has been taken and the numbers have been put together in a chart. Okay, so when we say data is normally distributed, we mean when you put it in a histogram, it's about this shape. Okay. So we're going to use this idea to answer questions, okay? And so I am going to cut and paste this picture onto the next screen, and we're going to use these percentage numbers to help us answer some questions, okay? So let's take a picture of that. Let's put it here. And we'll have this to look at while we're answering these questions, okay? So here's an example, and I want you to fill in your notes as we go. Part of your grade is going to be based on whether you filled in these notes. Alrighty. So the grades on a statistics midterm are normally distributed with a mean of 81 and a standard deviation of 5. Okay, so let's make sure we understand our terms here. Mean is mu, and standard deviation is sigma. Okay, draw and label the normal distribution curve. So I cheated and cut and pasted a nice, pretty, perfect curve here so I wouldn't confuse anybody, but draw one to the best of your ability, and then don't worry too much about it. We are going to label the exact middle. Okay, that's our mean of 81. Okay, the exact middle is the mean test score. And then we're going to chop it up like this. And so what I want you to do is try and find the point where this curve goes from being concave down to concave up. That's an inflection point. That looks to be about right here. Okay, that's guessing. But that's where your first standard deviation falls if you're trying to eyeball it. Okay, and it's symmetrical. So let's do the same over here. And then we know we've got to put two more little lines. The tail is tiny. This distance is going to be the same. So if I go the same distance over, it's about there, and the same distance over, it's about there. So space these out evenly once you get the first ones drawn. And it doesn't have to be perfect. Okay, so there's that one, there's that one, and there's that one. Okay, so standard deviation of 5. It's not always 5. I just picked 5 out of thin air, and then it happened to be in the example question also. But the mean plus 1 standard deviation, so plus 1 standard deviation is 81 plus 5 is 86. Plus 5 more is 2 standard deviations above the mean is going to be 91. And 3 standard deviations above the mean is going to be a 96. All right, on the minus side, 81 take away 5 is 76. That's minus 1 standard deviation. Minus 5 more is 71, so minus 2 standard deviations, and minus 5 more is 66. That's 3 standard deviations below the mean. Okay, so taking our percentages from over here, we can write them in our picture. 34% is within 1 standard deviation of the mean. 13.5% is within 2 standard deviations of the mean. And 2% is somewhere within 3 standard deviations of the mean, and then we've got 0.5% on this end and 0.5% on this end in that little bitty tail part. More than 3 standard deviations from the mean. Very few people do that. So what percent of this data falls between 76 and 86? Well, that's here at minus 1 standard deviation, and plus 1 standard deviation is going to be 34 plus 34, or a total of 68%. 8. There we go. Okay, so we're just going to look for the scores on the axis and add up the percentages. What percentage of the data falls between 71 and 91? All right, the fact that our numbers are matching up to the questions means we got them right. And so we need to add up all the percentages between 71 and 91. That's going to be 13.5, and 34 and 34, and another 13.5. All right, so I look at it this way. That's going to be 68. 13.5 plus 13.5 is 27. So that's 95%. And that agrees with our numbers on the previous page, that items within 2 standard deviations of the mean is 95% of the data. What you want to bet the next one is asking for within 3 standard deviations of the mean? Let's see. 81 and 91. Oh, no, they're getting creative on us. Okay, from 81 to 91, that's starting at the mean and going up to 2 standard deviations. So we're just going to add 34 and 13.5 to get the percentage of scores that fall between 81 and 91, and that's going to be 47.5%. If I could get over drawing it as a degree bubble, it might look right. Okay. And then what percent of the data is less than 86%? Okay, so there's our 1 standard deviation above the mean, 86. What percent scored below? We need to add up all the percentages below. Okay, so 34 and 34 is 68. 13.5 and 2 is 15.5, and another half is 16. So that's 84%. That lies less than 86 on the test grade. So that's how you do the percentages based on the empirical rule with a normal curve. All right, so I'm going to show you an application of this idea that helps you and where we might actually use normal curves for real-life scenarios. All right, you can't read Ted Williams' name over here. There we go. So here are 3 great baseball players. All right, and um, they are generally considered some of the best batters that have ever played the game of baseball, and they are Ty Cobb and Ted Williams and George Brett. And Ty Cobb played in the early 1900s, and Ted Williams played during the 40s, 30s, and 40s, with a break in the middle because he was a soldier in World War II, and then he came back to the game. And George Brett played in the 70s when I was a child, so I remember that name. And we want to look at the batting averages they had. So let's read here. 3 landmarks of baseball achievement are Ty Cobb's batting average of .420. That was his batting average for the entire season in 1911. And Ted Williams batted a .406 in 1941, and George Brett batted a .390 in 1980. All right, now you could ask who's the best batter, and everybody would say, well, Ty Cobb is because it's .420. And we don't want to say that that's a fair judgment because it says the averages can't be compared directly because the distribution of major league batting averages has changed over the years. Well, let's say that in practical terms. What could be different from the 1910s to the 1940s to the 1970s, which would make these batting averages not comparable? Could the rules of baseball changed? Could the technology of the bats have changed? Could the distance between bases have changed that make these numbers different enough that we can't really compare them? Any of those things could have happened and more. So we want an objective way to compare the averages because Ty Cobb did not play against Ted Williams, and so we can't compare them directly. We have to compare them against the people they played against. And so that's why we get the mean and the standard deviation of the batting averages of the entire Major League Baseball organization for these years. Okay, so let's keep going. The distributions follow a normal curve except for outliers such as Cobb, Williams, and Brett. While the men's batting average has been held roughly constant by rule changes and the balance between hitting and pitching, the standard deviation has dropped over time. So look at the means of the batting averages for the entire Major League Baseball organization, really close together. But this is the number that has dropped. So 3.7 percentage points. If I move this decimal over, I can read it as a percentage. The way that the averages are spread out in the 1910s, standard deviation was a higher number, so it was spread out more from the mean. So the averages got higher, much higher and much lower, or a little higher and a little lower anyway, because these numbers are still decently close. So 3.71% standard deviation in that decade, and then in the 40s, it went down a little. So that means the batting averages were all closer together that year. 3.26 percentage points was one standard deviation, and in the 1970s, 3.17. Did batting get more difficult? Did the rules change and make things harder to do well? That may be. I don't know enough about it to say intelligently, but I'm going to teach you a method of comparing these batting averages since they come from totally different populations, different years. There is an objective way to compare them. Okay, so this is called a z-score, calculating a z-score. So we're going to do 3, one for each of the players, and here's what we've got. A z-score is a number that you take the, in this case, batting average, whatever your data point is, I'm going to call it X, and you subtract the mean from it. So you know how far away from the mean that this score is, and then you divide it by the standard deviation, so you know how many standard deviations away from the mean that this score is. Can I say that again so it processes for you? You take your batting average and you subtract the mean batting average. Okay, so let's do this for Ty Cobb. So his batting average was given as .420. And the mean batting average for Ty Cobb in 1911 would have been .266 for his teammates and the rest of the people in the league. And then the standard deviation, the average amount that somebody fell away from the mean, was .0371. So this is the mean minus, or the data point for this person minus the mean. And that tells you how far away from the mean his average was. It was way far away. It was huge. And then when you divide by the standard deviation, it tells you how many standard deviations away from the mean that a data point lies. All right, I'm writing that down for you because it's going to be helpful for you understanding this. So we're basically figuring out where on that axis we could put this one score. Okay, so when you calculate this out, by the way, so for Ty Cobb, you get a z-score, and I did that here, of 4.15. Wow, we didn't see more than 4 points above the mean. Let's go back and look at this. Here's 3 standard deviations above the mean, and this little 0.5% tail are people that get more than 3 standard deviations above the mean. That's 0.5% of people. That's really a small percentage of people, and he got more than 4, so he's even farther out on this tail, which technically goes on forever. So he's really, really, really good. All right, so let's do the same thing for Ted Williams. All right, his mean from the problem was 0.406, and then the mean for people in his year was 0.267. And then the standard deviation for people in that decade was 0.326, 0.0326. So how many standard deviations away from the mean was Ted Williams? That's 4.26, even farther from the mean, even higher. So technically Williams was a better batter than Cobb, even though Williams' average was a little bit less than Ty Cobb. See, we're comparing them to the people they played against. They didn't play against each other, so that is a big piece of information there. All right, so then we deal with George Brett, and I bet everybody goes, oh, 0.390, that's definitely not the best one. I don't know yet. We can't judge yet. So let's subtract the mean from his day, which had gone down a little bit. So we could see that his was a little bit lower than these other two, 420 and 406. 390 is a little bit lower, but the average was a little bit lower. And then the standard deviation was smaller, so maybe that'll make up the difference. I don't know. Let's put these numbers in the calculator. I get 4.06. Okay, so yes, it's the lowest number and it's the lowest z-score compared to these other two, but it's not tremendously lower. He's still an incredible outlier, somebody whose batting average is just way out there above everybody in his day. And so how can we rank these 3? Well, Ted Williams comes out to have the highest z-score, so he is the best player among these 3 where batting average is concerned. Then Ty Cobb comes in second, and then George Brett comes in third, which is not at all the result we would have gotten had we simply looked at the batting averages given in the question. All right, so that's the kind of information that you can dig out of statistics, because a list of numbers doesn't tell you as much if you just have to look at all those numbers and make guesses from things. And so you're going to be calculating z-scores using this formula where z is the data point minus the mean of the data set divided by the standard deviation of the data set. And that number is going to be the number of standard deviations above the mean or below the mean, if it's negative, that a data point lies. So remember, this is where the value of your data point goes when you're looking at one data point at a time, okay? Okay, so in this case, we used the men's batting averages here compared with the mean batting average of the whole league and the entire standard deviation of the whole league. So use this formula to help you get through the work for this section.